Hello everybody. Welcome to the lecture series Foundation for VLSI Design. This is the 8th lecture. In this lecture, we'll be looking into CMOS inverter. Specifically, in this lecture, we'll be looking into the static characteristics of a CMOS inverter. We'll be looking into its gain, noise margins, and robustness. And we'll be also looking into the delay of a CMOS inverter. CMOS technology, or what is complementary MOSFET technology, is the most dominant technology employed for digital circuit implementation. And why CMOS technology is so popular? So the most important reason for it is that the gates implemented in CMOS technology, they draw almost zero power under static condition, right? And this is a very big advantage of a CMOS technology. And the among the components implemented in CMOS technology, a CMOS inverter is one of the most simplest, right? And therefore we should be understanding a CMOS inverter very well, because using the understanding of CMOS inverter, we can understand other types of logic gates which are implemented in CMOS technology also, right? So now let us look into how does a CMOS inverter look like, right? So CMOS inverter consists of a PMOS and an NMOS, right? So this is the schematic diagram of a CMOS inverter. So we have a PMOS or P type P channel MOSFET and NMOS or N type MOSFET, right? So these two are connected together. And if we look into the static characteristics of a CMOS inverter, by static characteristics means that we change the gate voltage, we sweep the gate voltage from 0 to VDD, right? So on this axis, the input voltage is VA, and we are increasing from 0 to VDD. And then observe that what is the output voltage or the voltage at this point, Vz, right? And we draw the curve. So this is the static characteristics of a CMOS inverter, right? So at each point, right, whenever we are applying a voltage, say this is the input voltage, right? So at the input voltage, this point, this is the input voltage, we can call it as VA, input voltage. At this point, we observe what is the output voltage, Vz, and we are obtaining this characteristics, this static characteristics, statically, right? So we allow the gate to reach a steady state before observing the value at the output pin, that is the pin Z of the inverter, right? So now let us first understand that how does a CMOS inverter produce this static characteristics. So first we let us understand that if we apply a voltage of 0 volt, right? We start with a 0 volt. That if we apply 0 volt, then what will be the output voltage at that is Vz, right? So when we apply a voltage of 0 volt, then the PMOS will be turned on while the NMOS will be turned off, right? So we can think that there is a path from VDD to this point, right? Since the PMOS is turned on, it will exhibit a low resistance and between the source and drain, and therefore we can think that VDD is directly connected to or it's connected to the point to the point Z through a low resistance path, and it will reach a voltage almost close to VDD, right? So when VA is equal to 0, then NMOS is off and PMOS is on, and the output Z gets connected to VDD through the PMOS, and therefore the load capacitance which is driven by this inverter, that will get charged to the supply voltage VDD, right? Now let us look into that what will happen if we apply a voltage of VDD to the input, right? So if this is we apply VDD at the point A, right, then we at the pin A, then the PMOS will be turned off and NMOS will be turned on. So if NMOS is turned on, this ground potential is connected to point Z through a low resistance NMOS, right, through this path, right? Now if this point, this Z was at higher potential, then and this capacitor was charged, it will get discharged through this NMOS, and finally the voltage that will be obtained at Z will be close to the 0 volt, right? So whenever input is 0 volt, the output will be around VDD. So we have got this characteristics from here, and the other point is that if the input is around VDD, right, so the output is around 0. So these 2 points are, we know, right? Now in between the both the transistor at the extreme point, that is the points that are shown by these crosses, at these extreme points one of the transistors is off, right? But in the intermediate region, both the transistors will be in the on state, and they can be either in the saturation region or in the linear region, right? So we'll get if we do the simulation and obtain a static characteristics, we'll get a curve something like this, right? So in the intermediate region, output is somewhere between 0 and VDD, and we can obtain the exact characteristics using simulation. Now let us look into the CMOS gain of a CMOS inverter. And in earlier lectures, we had seen that we had defined the point Vm as the voltage at which the input voltage and the output voltage are the same in a inverter, right? And we had said earlier that the gain is very high in a CMOS inverter at this point Vm. Now let us understand the reason for it, right? So we had said that at the point Vm there is a sharp transition in the output, and if we look into that, at which operating region the CMOS, the NMOS and PMOS are there at this point Vm, we'll find that both the transistors are in the saturation when it reaches the Vm point, right? So at the Vm point, both PMOS and NMOS are in saturation. Now what does that mean? What does that imply? So ideally, when both NMOS and PMOS both are in saturation, then drain current of NMOS and PMOS is independent of the drain voltage Vz, right? So note that the drain voltage is the Vz point, the output voltage, right? And in the last class we had seen, or last lecture we had seen, that if we draw the output characteristics of the MOSFET, on the x-axis we have VDS and on the y-axis we have IDS, then in the saturation region the current is constant, right? If the current IDS is independent of the voltage VDS, right? So the drain current of NMOS and PMOS is independent of the drain voltage Vz, right? So VDS is nothing but Vz in this case, right? So if the drain current is independent of the drain voltage, what it means is that the drain voltage can change arbitrarily independent of the input voltage VA, right? So the input voltage VA is controlling the gate the drain current, right? And the drain current is current is independent of this drain voltage, right? So it implies that the drain current can assume arbitrary value, and the Vz or the drain voltage can obtain can reach or take an arbitrary value irrespective of the drain current, right? So and therefore the ideal gain, which we defined as delta Vz by delta Va at the point Vm, will be infinite. Why it will be infinite? Because the output voltage Vz can change arbitrarily irrespective of what the input voltage is, right? So it can change arbitrarily with a small change in input voltage, right? And therefore the gain will be infinite. But in real CMOS inverter, this will be finite, and the reason is that the MOSFETs are not perfect, do not show perfect saturation. So in the last lecture we had seen that because of channel length modulation, uh, the the current in the saturation region depends on the drain voltage. It increases with the drain voltage, right? By the factor channel length modulation factor, right? So in practically there is a channel length modulation in the saturation, and therefore this will not be a perfect infinite slope here, but will have some finite slope, which is shown in this diagram, in this figure, right? So there is a finite slope in the static characteristics of the CMOS inverter, but this slope is still pretty high, right? And therefore the gain at the point Vm will be high, right? So the drain current of NMOS and PMOS depend on the drain voltage because of the channel length modulation, and hence Vz, drain voltage, depend on Va, and we obtain a finite gain in a CMOS inverter. Now, to keep noise margin high, we need to have this Vm point around VDD by 2, right? So this is VDD, this is 0 volt. So we typically want that Vm should be at VDD by 2, right? And this should be all, the output voltage will be VDD by 2 at Vm point, right? So to obtain this characteristics is a bit challenging, because we need to make saturation current of both PMOS and NMOS similar. But we saw that the saturation current depends on the mobility, right? Mobility of electrons and holes, and electrons have much higher mobility than the holes, right? So hence hole mobility, since hole mobility is lower than electron mobility, we need to keep the width of the PMOS more than the NMOS, so that the saturation current is the same for the NMOS and the PMOS, and we get the Vm point close to VDD by 2. Now, CMOS inverter and other CMOS circuits combine pull-up and pull-down networks in complementary symmetric configuration, right? So, in a CMOS inverter, the pull-up stage consists of only one PMOS, right? And in a CMOS inverter, the pull-down stage consists only of one NMOS, right? But in complicated logic gates, for example, say a NAND gate, NOR gate, or other types of CMOS logic gates, the pull-up network and pull-down network can consist of various more than one transistors, right? But the configuration or the topology in which these PMOS and NMOS transistors are implemented is what is known as complementary symmetric configuration, right? So when this kind of configuration is there, then the pull up network takes the output node to a voltage 1 logic or logic to a voltage of VDD or logic 1, and pull down network takes the output voltage to logic 0 or ground. But the topology is such that the under static condition, the output node is connected either to VDD or the ground. This node will either be connected to the pull-up network or to the pull-down network, and never to both, right? In the static condition, it will be connected to either the VDD or the ground through a low resistance path for any combination of bits at the input. So in a complementary configuration or complementary symmetric configuration, what happens is that um, in whatever the input combination is there. In this case, only two combinations are possible at the input, 0 or 1. But if there is multiple input CMOS logic gate, in that case, for all input combination, what happens that either the pull up network is on. If that is the case, then the point Z or the output Z will be connected to VDD through a low resistance path, right? Or if this the pull up network is not active or not turned on, then in that case the pull down network will be active, and in that case the output node Z, will be connected to the ground through a low resistance path, right? So under all input conditions and static condition, the output node Z will be either connected to the ground or to the supply voltage through a low resistance path. And what is the implication of this? The implication is that it makes output voltage more resilient to noise, right? Because if this voltage was directly connected to VDD through a low resistance path, it will be close to VDD, right? It will, even if there are some noise, because of noise the supply voltage will ensure that that noise gets killed, and we obtain a good voltage or good robust voltage at the output. Similarly, if this is connected to a 0 volt through or ground through a low resistance path, the path to the ground will ensure that even if there are some noises, those noises will be killed, and the output voltage will be fairly constant or at the ground voltage or 0 voltage. And this makes the CMOS topology or CMOS logic gates robust to or resilient to noise, right? And another important thing is that why CMOS technology has become so popular is because of its low power, right? So why CMOS technology or CMOS logic gates consume or dissipate very negligible power under the static condition? The reason is that in the static condition, at least one transistor is in the switched off state in the path from VDD to ground, right? So we said that whenever under all input condition, whatever the input condition will be there in inverter, there is only one input, only two possible input conditions, 0 or 1. But in complex logic gates in which there are multiple inputs, there can be several input combination. But under any input combination, what will happen is that either the pull up network will be switched off, or the pull down network will be switched off. And the implication of is that from the path from the VDD to the ground, at least one transistor will be in the switched off state, and that will actually uh, uh, um, 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 reduce the current from VDD to ground to almost zero. So and therefore a CMOS circuit draws negligible power from the battery under static condition. Why it is drawing with negligible power under static condition? Because from the path from VDD to ground, at least one transistor will be in the switched off state, and that will not allow the current to flow, and therefore the power dissipation will also be negligible or zero under the ideal condition. Now let us look into that what decides the delay of a CMOS inverter to a first approximation, right? So let us assume that the input is transitioning from high to low. So input is transitioning from high, that is VDD, to low, right, to 0 volt or ground, right? So when the input was VDD, right, the output was 0, right? And CMOS inverter, if the input is VDD, the output will be 0 volt, right? So output will be 0, and we expect that when the input becomes 0, the output reaches to VDD, right? So this is what we expect will be the waveform at the point Z, right? Now on what factors will this delay depend on? Delay of a CMOS inverter depend on, right? So we can assume that whenever the transition at the input happens from VDD to 0, the NMOS gets turned off. So initially, when the input was VDD, NMOS was on and PMOS was off, right? But when it goes to 0, when the input goes to 0, the PMOS gets turned on while the NMOS gets turned off. Let's assume that this happens instantaneously. If that is the case, then we can think that the equivalent circuit will be something like this, right? So PMOS is turned on, so there'll be some resistance of the PMOS, right, which we denote as RP, right? And the voltage at the point Z, that will rise from 0 to VDD through the charging by the supply voltage VDD, and charging will happen through this resistance RP. And whenever this transition has happened to 0 volt, the NMOS is turned off and therefore this switch is open, right? So now how fast this capacitor will charge, that will define the delay, right? If this capacitor charges very quickly, then the delay will be less. If this capacitor charges slowly, then the delay will be higher, right? Now, what will be the rate of charge or charging of this capacitor, right? So this is a simple RC circuit, right? And therefore, to a first approximation, we can say that the delay of that, or the time required to charge this capacitor, will be proportional to RC. RC here is the time constant, right? So the time constant is RC, and R is RP, or the resistance of the PMOS, PMOS in the inverter, right? And C is the load, or CL in this case, right? So to a first approximation, the delay will be proportional to the resistance of the PMOS and the load at the output, right? And if the transition is of the opposite type, meaning that the input is transitioning from low to high, right? If it is initially it was 0, right, and then it finally reaches to VDD. So when it reaches VDD, then the NMOS will get turned on, and PMOS will get turned off, because input is VDD, right? So we assume that this transition from 0 to VDD happens quickly, and NMOS turns on quickly, and PMOS turns off quickly, right? So when that happens, we can think that this capacitor will get discharged through through this equivalent circuit, right? So since the PMOS is switched off, this switch is open, right? And the NMOS is switched on, so we represent NMOS by a resistance, a low resistance Rn, right? Now initially it was, when the input voltage was 0, right? Input voltage was 0. This output voltage was 1, right? The output of the transistor, of the inverter, will be 1, and therefore this capacitor CL will be charged to VDD, right? And this capacitor will get discharged through the NMOS, right? So when the output voltage is reducing from VDD to ground, then the reduction or the discharging is happening through the NMOS, right? And to a first approximation, we can think, or we can consider, that the delay will be proportional to the time constant Rn into CL of this circuit. Right? Now, if we want to reduce the delay of a circuit, many a times we want that the delay of our CMOS inverter is less, right? And to reduce the delay of the circuit, what can we do, right? We need to reduce these things, these factors, right? Now, we can reduce the load, right? CL, that is being driven by a CMOS inverter. And the second way to do is to reduce RP, right, and RN. And how can we reduce RP? We can reduce it by increasing the W by L of the PMOS, meaning that we widen the size of the, or increase the size of the of the PMOS. And similarly, we can reduce Rn by increasing the width of the NMOS. So if we want to, if we increase the width of the PMOS or NMOS, the corresponding the delay will decrease, right? That is what we expect, right? So this is very simplistic model for the delay of a CMOS inverter, but these things are the most basic or fundamental thing that you should be familiar with for a CMOS inverter, so that you can use these concepts later in advanced courses. If you want to know more about CMOS inverter, you can look into these references. Now, to summarize, what we have looked into in this lecture is a CMOS inverter. We looked into the static characteristics of a CMOS inverter. We looked into that why the CMOS inverter has a high gain at the point Vm, and we also looked into that why there is the static power dissipation in a CMOS inverter is negligible, and why it is more robust or resilient to noises. And we also looked into that to a first order on what factor the delay of in a CMOS inverter depends on. So that's it for this lecture. Thank you very much.